Okay, so for a long time, astronomers were interested in categorising stars. So they decided to build a system based on the temperature. So here you have different categories of stars, so O, B, A, F, G, K, M, where O is the hottest stars and M are the coolest. So O stars are very hot, so they're also extremely luminous. Most of their radiation is in the ultraviolet range, and because they're so hot, they have really short lifetimes. G, that's our sun. They have typically calcium-2 lines in their spectrum, so they're quite low on the heat spectrum, but they'll last a long time. M-class stars are the most common in the main sequence, so 75% of stars are M-class. They've got very low luminosity, so they're unable to be seen by the naked eye, but they're also cool enough to have metal oxides in their spectrum.
In the early 1900s, Hans Rosenberg published a diagram plotting the apparent magnitude of stars in a cluster against the strength of spectral lines. These spectral lines serve as a proxy for the temperature of the star, an early form of spectral classification. Hertzsprung in 1911 published diagrams using apparent magnitudes of clusters of stars at the same distance, and Russell's early versions of the diagram a couple of years later included the measured distances of the stars and thereby obtaining absolute magnitudes for these stars. So this diagram is effectively a plot of luminosity against temperature, so an HR diagram. The HR diagram represents a major step towards understanding how stars evolve over time. Numerous stars are observed at various stages in their life cycle to determine their changing properties and probable evolutionary tracks.
This is the HR diagram, as famously implied. Both the axes, the y-axis scale is luminosity relative to the sun. So for example, at 1, that's 1 lots of the luminosity of the sun. 10 squared would be 100 times the luminosity. These are the luminosity of the stars, so the power output. So the units is watts per square metre. The x-axis is in terms of temperature, which is going down by scale factor for half. And that's ranging from 40,000 to 2,500 degrees Kelvin. You have different groups here which are going to be explained: white dwarfs, main sequence, red giants and red supergiants. And if I haven't mentioned already, the y-axis is a logarithmic scale.
Where stars spend most of their time is the main sequence, and they spend about 90% of their lifetime here. And in this region, they fuse hydrogen into helium, and the most famous star here is the Sun, which is here.
Up here we have the giant stars, and they have a substantially larger radius and luminosity than a main sequence star of the same temperature, and that's why they are above the main sequence here. And red giants form when stars run out of hydrogen to fuse, so the star will begin to collapse on itself due to gravity, and the temperature will increase, so eventually the star will start to fuse helium into carbon. And then it will expand to many times its original size.
Just above them is the red supergiants. These are the largest stars. They're the brightest as well and the most luminous. And in this region they continue to burn helium, and the most famous star here is Betelgeuse.
Once stars have exhausted their nuclear fuel, they expel most of their outer material, and this leaves only a hot core. The hot core of the star is what we call a white dwarf, and it burns initially at about 100,000 Kelvin and then cools down over the next billion years. One famous white dwarf that's quite close to us is Sirius B.
Diagrams like this to work out the sequence of a star by using a lot of the luminosity against the temperature. And so when you know that a certain luminosity, say times 10, r star times 10 to the 2, you can work out that any star that's going to be at this luminosity is going to be main sequence, but it will only have a temperature range of approximately like 7.5 to about 3,000 Kelvin.
Right, and there's an equation called the Stefan-Boltzmann law which relates to luminosity and temperature. And what's useful about this law is if the luminosity and temperature are both known, then you can rearrange this equation to find the radius of the star. And when you know the radius of the star, you can find out a bunch of